Once the most precious metal in the world, it covers the top of the Washington Monument and the wings of high-performance aircraft. It can bend like paper and support like steel. It's aluminum, and everything you need to know about it is right here, now, on How Stuff Works. Every year, we make enough aluminum foil to cover the state of Maryland. But why? What is it about this silvery metal that makes it the ultimate material for everything from baking potatoes to going to space?
Aluminum is probably one of the most precious metals we have.
Yeah, you're good and square there.
It's everywhere, and there's a reason for it. It is such a versatile material.
It turns out that aluminum has some amazing qualities.
It combines all the characteristics required to be more versatile for design, and aluminum provides all of those aspects. Aluminum is the metal of the future.
In fact, it's pretty much impossible to go a day on the planet without aluminum. But even though we use it all the time, this super metal still has its secrets. Aluminum surrounds us. It's even in us. A typical adult takes in 30 to 50 milligrams of aluminum every day from our food and drinks. Not that it's nutritional, it's just impossible to avoid. Aluminum is the most common metal in the world. In fact, it makes up 8% of the planet's crust. But that doesn't mean it's easy to find, at least not in its pure state. Unlike gold and silver, it doesn't exist as raw nuggets or rich veins. No miner has ever panned for aluminum.
We don't find aluminum in its free form, but it just doesn't look like aluminum.
That's because aluminum has a long-running atomic love affair with oxygen. It just can't live without it. And oxygen is the third most common element in the world. That means that without some serious energy to stop it, aluminum automatically bonds with oxygen to form aluminum oxide instead of staying in its pure form. So when you go looking for aluminum, you're pretty much looking for mud, or at least clay. In fact, aluminum's first recorded use was by ancient Middle Eastern potters who used clay, laden with aluminum oxide to strengthen their pottery.
It's been around forever, 5500 BC, they talked about the metal from clay, but there was no process that you could get the quantities that would make it feasible.
In other words, it was just clay, not metal. But it wasn't until 1807 that British chemist Humphrey Davy first identified a metal base to the salt called alum. While identifying it was the easy part, isolating the metal proved to be the real challenge. It took almost another 20 years before anyone actually did it. But the process was so difficult and expensive that it kept aluminum more valuable than gold until the beginning of the 20th century.
Selling for, in today's dollars, about $600 an ounce. Napoleon III entertained guests with, he used an aluminum spoon and the guests used gold, but the aluminum spoon was considered more valuable.
Today, the process of isolating aluminum begins with a rich deposit of that same ancient clay, bauxite. Alcoa's Huntly Mine sits just south of Perth, amid Australia's darling mountain range. And these mountains are pretty much built from bauxite.
They're found on the mid to the upper slopes of the ranges here. This is the largest bauxite mine in the world. Here we mine 23 million tonnes of bauxite every year.
But most of it can't be removed without first busting through a barrier of underground rock that's more than 16 feet deep. And how does that happen? With enough explosives to demolish a 10-story building.
We'll have about 1 to 2 hectares as a blast every time, and that will liberate in the order of between 50 and 100,000 tonnes.
That's 50,000 tons of ore, not aluminum. Now, the trick is to separate the aluminum and oxygen from everything else inside the bauxite, which means pummeling the ore into powder.
The milling system produces fine particles that's easy to digest.
The powdered ore is digested at facilities like Alcoa's Pinjarra refinery. That's where an amazing transformation takes place. The bauxite powder is mixed with a caustic fluid that physically separates the aluminum oxide from the mud and sand, leaving a solution of concentrated aluminum oxide. And here's what's really astounding. The solution dries into gritty crystals called alumina that look more like table salt than the metal it will eventually become.
Aluminum oxide is a white, it resembles beach sand. It's extremely bright, it's extremely hard. As a matter of fact, if you go to the construction supply store and buy sandpaper, you're buying aluminum oxide.
But you won't find this aluminum oxide down at the local hardware store. It's feeding the global demand for aluminum. That's why it's critical for it to get shipped as quickly as possible. Any delay in the supply chain drives up the cost of aluminum. So at Alcoa's Bunbury port, conveyors transport the alumina using a massive ship loader.
The ship loader is one of our most strategic pieces of equipment within the organisation. Really, it's if the ship loader does not work, we don't load out any alumina, which is our bread and butter.
The loader fills ships with up to 70,000 tons of alumina. The freighters are divided into 7 massive hulls. Why 7? Because the world's demand for aluminum is so great, ships are filled to the brim, and it's critical that the colossal weight of the alumina powder be distributed evenly across the entire length of the hull.
If we get it wrong, the vessel could break. We load in small increments, if you like, up and down the vessel until we sail at a good level.
Currently we've got another 550 tonnes to put on the starboard side, and that hold will be finished.
A loaded ship leaves the port every 3 days, and the alumina it carries will be transformed by a smelter into 35,000 tons of pure aluminum, the metal that makes our way of life possible. Drag racing, the fastest sport on land.
So that's picking them up and putting them down.
188.52 miles per hour.
I love the speed, I love the thrill, I love the excitement.
In drag racing, it's not just top speed that matters, but acceleration. And there are 2 ways to boost it. You can add horsepower, or you can cut weight.
Lightweight is crucial because it essentially equates to extra horsepower.
Without this aluminum technology, this motor would have to weigh, I'm going to say, in the neighborhood of 800 pounds.
But pure aluminum suffers from 2 crucial weaknesses. It doesn't have the heat resistance that steel does. It's hot inside the piston cylinders. And aluminum's much softer than steel, which makes it great for punching out beer cans, but bad for standing up to high-pressure explosions.
We're putting a lot of stuff in the cylinders on these things to make them really try to blow up and expand.
It's not just the pressure from inside the engine that's a problem. As the dragster accelerates from 0 to more than 200 miles per hour in less than 6 seconds, thrust twists every piece of the car, including the engine block.
As it's twisting, trying to twist this whole frame up here, the block is kind of helping hold this whole car together too.
But if the block isn't strong enough, the twisting force pinches the piston cylinders inward. and causes real trouble.
It's going to gall the piston, it's going to start rubbing the cylinder walls, and it's going to eventually blow up.
So how do engine builders overcome aluminum's weaknesses? By blending specialized aluminum alloys. And here's what's so remarkable about the metal going into these engines. It's 98% aluminum. Just by adding tiny amounts of copper, silicone, magnesium, or titanium, it's possible for companies like Dart Machinery in Troy, Michigan, to build lightweight aluminum alloy motors with heavy-duty strength.
Which all change the properties of the metal, giving it hardness, giving it tensile strength, giving it good elongation and fatigue resistance.
The other tricks are in how you shape and treat the aluminum alloy. The traditional method of making engines was to pour molten aluminum into a mold. But this leads to structural weaknesses in the metal.
You done know cast aluminum blocks was not a good quality piece to use.
To solve that, machinists now mill each engine out of a single 700-pound billet of compressed aluminum alloy.
After it's poured molten into a shape is forge, which is an impact process which condenses it into a cube and also condenses the grain structure and the molecular structure, making it very dense, very solid, and very uniform.
But actually carving an entire engine block from a dense alloyed metal is no easy job. Which is why Dart calls in a high-tech machine called a CNC.
CNC is computer numerical control, and that refers to the fact that a computer program is driving all of the cutting tools in the machining center.
The CNC attacks the billet with a series of sharpened carbide steel drill bits. The much harder steel blades easily shape the lighter and more pliable aluminum, all according to a tricked-out 3D design.
When we rough the blocks, we'll machine like the roughing tools will run 4,000 RPM, 240 inches a minute. We can make 1.5 yards of chips in 2.5 hours.
They remove a lot of metal in a short amount of time.
By the end, the 700-pound billet is whittled down to an engine block weighing just 140 pounds. But before the engine is ready for the heat of competition, it undergoes a final process. Each engine spends 12 hours in a 300-degree oven. The process is called heat treating, and it does something remarkable to this once solid cube of aluminum.
The heat treating process aligns the molecules, the grain structure of the metal, and it ultimately makes it a much stronger, much more uniform, and much more stable piece.
The entire process produces aluminum engines strong enough to pound out more than 2,100 horsepower, almost 3 times as much as a NASCAR racer.
Everybody's going more with a billet product. It's more expensive, but it's better.
A finished aluminum engine costs as much as $120,000. But for veteran drag racer Ricky Smith and his daughter Melissa, the aluminum engine forms the heart of the family race team. And every day at the track in Winston-Salem, North Carolina, Smith Racing pushes the limits of both man and metal.
80% of this thing is made out of aluminum.
Without aluminum, drag racing would probably be set back 40 years in terms of technology.
Dragsters match the speed of a jet on takeoff. Whether at the track or on the tarmac, aluminum gets these machines where they need to go. light, strong, and formable. Aluminum is a high-tech material that has some very down-to-earth uses, and one of them fits perfectly in the human hand: the beer can.
It's a very efficient package.
It's a perfect container.
It turns out that beverage cans are under some serious pressure. The average beer can exerts outward pressure of 95 pounds per square inch, about 3 times as much as a car tire. And the only thing containing that pressure is a wall of metal just 4/1,000th of an inch thick. That's thinner than a piece of paper.
If you try to squeeze it, you can tell it's not just full of product, but it's a little bit under pressure. That's a natural aspect of the carbonation process, and it keeps the integrity and the quality of the beer at its highest state.
So how does aluminum hold back the explosive power of beer? By taking on the exact right shape. At Anheuser-Busch's Metal Container Corp in St. Louis, Missouri, the transformation into a container begins with 16,000-pound coils, when the coil unrolls and a punch knocks out flat half-ounce discs about the size of a coaster.
We've been able to use just barely enough metal to make sure that we have a good, high-integrity package.
Each tiny disc is then stretched to become a full 12-ounce beer can. Incredibly, aluminum can take this pounding without tearing or breaking. Because it's so ductile, it doesn't even need to be heated to take on a new form.
It really allows the product to stay fresher than most packaging materials, and that's the beauty of the aluminum.
The stretching is done by a cylinder press that slams into the disc. The force of the impact draws the metal out an incredible 400 times its original height and creates a 12-ounce container. But it still doesn't have a top. So pallets holding 8,169 cans are shipped out to breweries and soda companies where each is filled and capped.
It's 2,000 cans a minute per line, so we're filling 10,000 cans a minute throughout the day.
10,000 cans a minute means 100,000 six-packs of beer each and every hour of the day. Let's say you wanted to design the ultimate material. Lightweight, malleable, non-corrosive, strong. It would look a lot like aluminum. A whole lot. But to get pure aluminum, you've got to rip away the oxygen atoms that it holds so tightly. And the way to do it is with electricity. Lots and lots of electricity. Which is why the most difficult part of producing aluminum isn't mining the bauxite or building facilities like this, Alcoa's Point Henry smelter in Geelong, Australia. It's generating electricity needed to make the whole operation run.
They call aluminum electricity in a solid form, okay, because it takes so much. About 30% of our cost to make a pound of aluminum is just in electricity.
We use over 340 megawatts of electricity a year.
Which means that each pot of aluminum is constantly blasted with enough electricity to power a mid-sized city.
The power comes into basically the top of each pot, flows down the anode rod, through the pot, then flows out the bottom and then onto the next pot. So it's a long series circuit.
But what is the electricity doing to the alumina inside the pot? It turns out that the force of the electrons in the circulating electricity literally shatters the bonds between aluminum and oxygen.
It's in the presence of electricity that electrolytic process happens, that we free up the aluminum atoms from the oxygen atoms.
The oxygen rises to the top of the pot, while the denser molten aluminum sinks. The 1742-degree liquid aluminum is sucked out of the cryolite with a vacuum.
The aluminium's removed from the pot via the tapping operation. That happens once every 36 hours, and we take out over 2 tons of metal every 36 hours.
Finally, work that started with a bang at the bauxite mine is complete. To keep up with demand, this operation runs 24/7 and pumps out more than 154,000 tons of aluminum a year. But what exactly makes pure aluminum so useful? Turns out, its incredible abilities come from the unique way aluminum atoms group together.
If you can imagine a square box, in the center of each of the 6 sides is an atom, as opposed to being in the center of the whole cube.
The aluminum atom can be pulled and stretched from any direction. Its cubic structure lets anything made from aluminum expand and contract in all directions without breaking.
It can be rolled, hammered, stamped, beaten to death.
Not bad for the 5th lightest metal in the world. Lithium, beryllium, sodium, and magnesium are lighter, but none form atomic bonds that are both strong and flexible. So aluminum is the only metal with a low atomic weight that's also durable enough to hold up under the most extreme conditions. Aluminum's lightweight and relative strength make it an ideal metal for all kinds of different applications. But for one, it is essential. There can be steel beer cans. They don't make steel planes. A Boeing 777 is more than 200 feet wide, 242 feet long, and weighs 370,000 pounds. Its engines generate more than 230,000 pounds of thrust. Its top speed is 553 miles per hour. That's more than twice as fast as the worst hurricane winds in history. And only aluminum makes all this possible.
The aviation industry uses it to a tremendous degree for everything. All aviation materials are closely monitored. They're inspected, x-rayed, licensed, they're kosherized.
Because of its unique atomic structure, aluminum has an amazing strength-to-weight ratio. A 777 built out of steel would weigh almost 1 million pounds. To make it fly would require engines as powerful as 3 third-stage Saturn V rockets, generating more than 500,000 pounds of thrust. But it's not just that aluminum is light and requires less power to fly. It's also very flexible, which is ideal for making airplane wings.
When you look out and you see the wing flexing, just relax and know that it's meant to do that.
So you've got to have the ability for those wings to give and take as the plane lifts off and lands.
But it turns out that the only thing keeping all of this flying metal together is an invisible microscopic layer of oxygen. When pure aluminum comes in contact with air, it immediately oxidizes, forming a microscopically thin skin of aluminum oxide.
It's very important to protect it against the elements of nature and factory air.
But how do you make a sheet of aluminum that can stand up to the rigors of flight? The answer is found here at Alcoa's Davenport Works in Davenport, Iowa. More than 2,200 men and women work around the clock in this 130-acre facility.
It's really like having a small city under one roof.
The work begins in the plant's furnace, where the company creates a special alloy. Aluminum mixed with small amounts of copper, zinc, iron, and magnesium. The molecular bonds within the alloy stretch longer and thinner than plain aluminum, while remaining flexible and strong.
Alloys are selected based on their composition and their characteristics.
Get all those different possibilities for that particular piece of aluminum.
But to create those powerful bonds requires some serious heat. The furnace roars at 1,400 degrees and occasionally coughs out molten metal. Just one drop on bare skin burns through flesh. So workers don't take any chances.
It keeps the metal off of my neck, and trust me, you need it, because the metal and the heat here is so intense, you can't go near it without some kind of protection.
From the furnaces, the aluminum alloy pours into giant water-cooled molds. This aluminum may end up as thin, sleek airplane skin, but it starts out as an ingot more than 29 feet tall, 6 feet wide, and 1.5 feet thick. Think about that. The thin skin on a jet wing starts out as a giant aluminum brick as tall as a 2-story building, and just one ingot weighs 35,000 pounds, more than 2 fully fueled Learjets. They're so heavy, specially trained operators must lift them using 50-ton cranes.
You cannot think, you just got to react. It's not up, down, right, left, you just do it. You have to be the crane.
How do you turn these massive hunks of metal into wing skin? It takes one of the beefiest machines on the planet, a 7.5-ton beast called a hot rolling mill. At 220 inches, the mill here is the widest in the world. But why is wider better? It's because the wider the sheets, the fewer it takes to cover a wing. And fewer panels means fewer seams, and that equals a stronger wing.
It's a real beast. And what that does is allow us to make very long, very wide pieces for customers, which gives them a more structurally sound piece.
To create those pieces, the mill generates an incredible 16 million pounds of force. That's as much force as a space shuttle's engines generate on liftoff. Only instead of hurling the shuttle into space, this press pushes out perfectly flattened sheets of aluminum.
It's like putting the dough in one end of a pasta machine and squeezing it out the other.
We might send out something that's 3/4 of an inch, and its eventual final shape can be down to as thin as 1/4 of an inch.
But it's not just power. The work must also be incredibly precise. Tolerances on the roller are less than 1/1000th of an inch and are capable of stretching over 65,000 pounds of aluminum at once. That's because the lives of more than 300 people are on the line every time a full 777 takes off.
Voids or defects in the metal that could, cause the metal to fail at some point.
These sheets form both the upper and lower skin of the wing. The aluminum alloy for the upper part has to endure the force of air moving across it at nearly 600 miles per hour.
Upper wing skins of aircraft are typically 7000 series alloys, and those are selected for their high strength.
The lower wing skin needs to be even stronger to repel debris kicked up by takeoffs and landings.
All of those things that happen underneath the wing. The underside of the wing gets pretty beat up.
Too soft and the wing skin will damage easily. Too hard and it won't flex. These raw aluminum sheets strike the right balance before they move on to the largest factory in the world, where they're to be assembled into the cutting-edge 777 aircraft.
Ready to go. So take a look.
Bulletproof glass. Since World War II, laminated glass has offered the best protection available against enemy rounds. But what do you do when bulletproof glass isn't bulletproof?
Bulletproof glass that in many applications where the enemy is getting more creative, it does not work.
A 50 caliber round is one of the most devastating tools of war.
50 caliber means it's 0.5 inches in diameter, but the 50 caliber slug is almost 2 inches long. It could actually hurt somebody probably just by throwing it at them. I mean, these are significant bullets.
Fired from a sniper rifle or other special weapon, these rounds achieve muzzle velocities of 2,800 feet per second. Even at a range of up to a mile, the round can punch through light armor and even bulletproof glass. Like a rock through an old school window.
We actually had an instance where we tested a 3-inch all-glass laminate, and the bullet went straight through the laminate, it penetrated 5 phone books, and rattled around the test cage for a while before finally stopping.
So how do you protect against something so powerful? The answer, aluminum. Unbelievably, the same aluminum oxide smelted into metallic aluminum can be transformed into the ultimate bullet-stopping material. It's a see-through aluminum panel called Alon.
Simply put, it's a better armor material.
But how can white, powdery aluminum crystals become clear, bulletproof panels? It's all thanks to aluminum's unique structure. Only in this case, it's not the flexible metallic cube. It's a specialized crystalline form.
You have a defined structure, defined geometry, defined placement of atoms.
Unlike in a metal, this structure doesn't flex or bend. Instead, it shatters on impact. This might seem like a weakness, but the crystalline structure of the ceramic molecules actually gives Alon its bullet-stopping strength. How? because with each crack and fracture, the panel drains a bullet's deadly force.
It absorbs the energy from the bullet, and it'll break it up into smaller pieces so that it doesn't even penetrate the laminate.
Alon gets its name from its key ingredients, aluminum, oxygen, and nitrogen. And all three are combined into a dried powder here at Surmet Corporation in Burlington, Massachusetts. And here's what's so surprising. Alon panels are made like ceramic pottery, with the powder pressed into molds and fired in a special kind of kiln.
It's very hot indeed. And we are talking well over 1,000 degrees, approaching 2,000 degrees.
This is where a miraculous transformation occurs. The aluminum, oxygen, and nitrogen atoms fuse together into a ceramic with 100% density.
When you're looking through something and needs to be clear, you cannot have any microporosity, even on the level of atoms.
It also needs to be completely pure. But you can't see through it yet, so each panel is ground and polished until it's fully transparent.
You can see that milk-like material is a polishing compound that goes between the polishing pads, and it sits on here for many hours because the material is so hard, and it has to be ground down smooth.
Finally, the panel is ready to be tested against a deadly round on the battlefield, the .50 caliber.
On the back side here, you can see that there's a bulge, but there's no hole, and that this did prevent the bullet from penetrating it.
Not only did this aluminum panel stop the round, but this material is lighter, thinner, and tougher than a similar sheet of bulletproof glass.
I know it'll be saving a lot of lives. A lot of soldiers' lives. They put their lives on the line for us, and these materials will help them out a lot.
Every day, Americans go through more than 1 million pounds of aluminum. But for much of this mega material, it won't be its first time around.
It's so recyclable. About 2/3 of the aluminum that's ever been made is still in existence.
While it may take a lot of power to make aluminum, once aluminum oxide is stripped of its oxygen atoms, metallic aluminum is incredibly stable. That means it can be melted down and reused again and again, forever.
Aluminum is like a pig. Nothing goes to waste. Everything's recycled.
Recycled cans wind up in a place like this, Anheuser-Busch Recycling Corp. In Hayward, California.
About 6,000 pounds in there. We're gonna open these doors. Cans are just gonna fall out. After he dumps all this, I'll get my guy, Robin. We'll just push these cans up, push them on the conveyor. We got Jose up there sorting material.
Every loose scrap of paper, piece of steel, or plastic, anything that's not aluminum, needs to be removed.
We try to do the best inspection we can, so we ship these to the mills and get the best loads out that we can.
After inspection, the loose cans fall into the crusher, where a massive hydraulic press crunches them into bales that are perfectly square. Then they're shipped off to the smelter.
They're going to be melted down and made into new aluminum can sheet.
And here's a staggering fact to ponder with friends over a beer. In less than 3 months, an aluminum can circulates once through its life cycle.
That can be all the way through that closed loop system and back in your refrigerator 60 to 90 days later, filled with a new beverage.
All while using much less energy. In Australia, smelters alone consume 10% of the nation's total power. So by recycling, you cut the demand for electricity, and that reduces greenhouse gas emissions.
Recycling an aluminum can saves about 95% of the energy required to make a can out of virgin materials.
.50 caliber rounds aren't the only danger in a war zone. IEDs, or improvised explosive devices, have been the leading cause of American casualties in the Middle East. More than 1,700 U.S. personnel have been killed by IED explosions since 2003. Unlike the penetrating power of a high-speed projectile, IED's killing power comes from concussive force, a massive rolling wave of energy that can shred a Humvee and anyone inside it.
It's blast that is one of the big threats now, not just projectiles.
Amazingly, aluminum may hold the answer to protecting against these deadly blasts. The key? Bubbles. Just outside Toronto, Canada, Cymat Technologies is engineering a low-density, air-rated aluminum known as aluminum foam.
We really want to get our material between harm and people.
Creating aluminum foam isn't easy. It means transforming an 800-pound block of aluminum into 4x8 panels with a total combined weight of just 40 pounds. It takes place inside a special chamber that creates bubbles in the molten aluminum.
That little box you see over there, that's where all the magic's made.
We can adjust the airflow and the RPM and the temperatures and the speed of production to change the properties of the foam. We can make a light foam, we can make a very heavy foam, large cells or small cells.
The smaller the cells or bubbles, the heavier the foam. Lighter foam can be installed in car doors. The heavier stuff might one day form the inside walls of the U.S. Embassy in Iraq. And no matter the weight, it's all designed to do the same job.
As the impact hits it, each one of those bubbles, the walls collapse, and as they fracture, they're each absorbing a little piece of the energy that's being impacted on the panel.
As each bubble in the foam collapses, it takes away energy from the blast. So instead of the concussive force from an explosion ripping into a building's support columns or human tissue, it's absorbed by strategically placed foam.
Force will actually compress the material and not transfer into the other structure. And that's exactly what our material is great at doing it.
Bulletproof glass and foam aren't the only ways aluminum fights terrorism. It also powers bomb-detecting lasers with X-ray vision. More than 7 million cargo containers enter U.S. ports every year. With this flow of commerce comes the risk of terrorists smuggling an atomic bomb into the country. That's why scientists are rushing to create a laser-based device capable of detecting nuclear materials before it's too late. And this important work couldn't happen without aluminum.
If it weren't for aluminum, we would not be able to do the type of research that we're doing right now.
You look into the endless possibilities, it really is amazing.
Scientists have long known that as magma cools within the Earth's crust, aluminum and oxygen atoms crystallize to form clear corundum, the base mineral for sapphires. This means the aluminum and oxygen atoms pack into a regularly ordered and repeated molecular pattern. Imperfections within the structure refract light in ways that give sapphires their brilliant colors.
Is these gorgeous Ceylon sapphires that you find in the ground actually have impurities that cause that blue color or that yellow color.
So what do sapphires have to do with lasers? Well, researchers discovered that by combining aluminum with another metal, titanium, it's possible to synthesize perfectly clear sapphires. And instead of refracting light, these sapphires amplify light pulses into lasers strong enough to penetrate metal containers and scan what's inside. Laser stands for light amplification by stimulated emission of radiation. So while the light of the sun or lamps beams outward as dispersed wavelengths, lasers focus light into a beam with an incredibly short wavelength. And the crystal structure of Thai aluminum sapphires not only focuses these beams, it actually amplifies their power by increasing the frequency of the wavelength.
You have amplifiers which crisscross back and forth through the crystal, and each time the beam goes through the crystal, it gets more energy. And this is the basis for our laser.
But where do you get a 45-pound sapphire? That's nearly twice as large as any found in nature. To produce one of these massive synthetic gems, Crystal Systems in Salem, Massachusetts combines aluminum, oxygen, and titanium in a process designed to replicate forces inside the Earth's crust. And it all starts with pieces of aluminum sapphire seed crystals called crackle.
It's really the building blocks, if you will, for the growth and the crystallinity of our sapphire.
At 3,812 degrees Fahrenheit, more than twice the melting point of steel, the crackle melts and blends with the titanium. Then, remarkably, as the mixture drops just below this incredibly hot temperature, it freezes.
The process itself is a very simple process. We're melting things and we're freezing them.
We slowly bring it down to a point where it solidifies. Then, once it's solidified, we open it up and we take out a crystal. This is titanium crystal.
The sapphires are then cut and polished, making them ready for use inside the world's leading research centers. At the Lawrence Berkeley National Laboratory in California, Thai aluminum sapphires amplify light energy to astounding levels.
This is higher than the electrical grid output of the entire world.
This incredible energy is only available as a focused laser, beamed in short bursts. And these bursts are powerful enough to penetrate all kinds of things, including metal shipping containers where terrorists might plant dangerous weapons.
Those beams can detect nuclear materials, concealed nuclear materials in containers, and could be useful, for example, for scanning cargo ships coming into ports to ensure that no nuclear material gets shipped into the U.S.
Because if there are nuclear materials present, the radiation will interrupt the beam in a unique way. And this interruption will send a warning signal back to authorities. Abundant enough to turn into beer cans. Strong enough to power dragsters. Flexible enough to skin airplanes and transformable into everything from glass to foam. Aluminum is the ultimate material for the modern world. And this is just the beginning of the secrets held by this miraculous metal. Same ancient clay, bauxite. Alcoa's Huntley Mine sits just south of Perth, amid Australia's darling mountain range. And these mountains are pretty much built from bauxite.
They're found on the mid to the upper slopes of the ranges here. This is the largest bauxite mine in the world. Here we mine 23 million tonnes of bauxite every year.
But most of it can't be removed without first busting through a barrier of underground rock that's more than 16 feet deep. And how does that happen? With enough explosives to demolish a 10-story building.
We'll have about 1 to 2 hectares as a blast every time, and that will liberate in the order of between 50 and 100,000 tonnes.
Once the most precious metal in the world, it covers the top of the Washington Monument and the wings of high-performance aircraft. It can bend like paper and support like steel. It's aluminum, and everything you need to know about it is right here, now, on How Stuff Works. Every year, we make enough aluminum foil to cover the state of Maryland. But why? What is it about this silvery metal that makes it the ultimate material for everything from baking potatoes to going to space?
Aluminum is probably one of the most precious metals we have.
Yeah, you're good and square there.
It makes up 8% of the planet's crust. But that doesn't mean it's easy to find, at least not in its pure state. Unlike gold and silver, it doesn't exist as raw nuggets or rich veins. No miner has ever panned for aluminum.
We don't find aluminum in its free form, but it just doesn't look like aluminum.
That's because aluminum has a long-running atomic love affair with oxygen. It just can't live without it. And oxygen is the third most common element in the world. That means that without some serious energy to stop it, aluminum automatically bonds with oxygen to form aluminum oxide instead of staying in its pure form. So when you go looking for aluminum, you're pretty much looking for mud, or at least clay. In fact, aluminum's first recorded use was by ancient Middle Eastern potters who used clay, laden with aluminum oxide, to strengthen their pottery.
It's been around forever. 5500 BC, they talked about the metal from clay, but there was no process that you could get the quantities that would make it feasible.
In other words, it was just clay, not metal. But it wasn't until 1807 that British chemist Humphrey Davy first identified a metal base to the salt called alum. While identifying it was the easy part, isolating the metal proved to be the real challenge. It took almost another 20 years before anyone actually did it. But the process was so difficult and expensive that it kept aluminum more valuable than gold until the beginning of the 20th century.
Selling for, in today's dollars, about $600 an ounce. Napoleon III entertained guests with, he used an aluminum spoon and the guests used gold, but the aluminum spoon was considered more valuable.
Today, the process of isolating aluminum begins with a rich deposit of that.
It's everywhere, and there's a reason for it. It is such a versatile material.
It turns out that aluminum has some amazing qualities.
It combines all the characteristics required to be more versatile for design, and aluminum provides all of those aspects. Aluminum is the metal of the future.
In fact, it's pretty much impossible to go a day on the planet without aluminum. But even though we use it all the time, this super metal still has its secrets. Aluminum surrounds us. It's even in us. A typical adult takes in 30 to 50 milligrams of aluminum every day from our food and drinks. Not that it's nutritional, it's just impossible to avoid. Aluminum is the most common metal in the world. In fact,